Wie? Hallo?
Okay, before we start the first afternoon session, I repeat an announcement that Rafaela made already. So today and tomorrow there will be public talks. Today a public talk by Netta Englert, tomorrow a colloquium by Annie Strominger, and both take place at 7 p.m., but not here. They will take place in the festive lecture hall of the Austrian Academy of Sciences. So you see the address up there. And today, in case you want to join the group, we're going to leave at 6:20 p.m. and we're departing from in front of the university building, so near the stairs where the testing box is, and you will be accompanied by Harald Skake and Ben Koch. And if you want to go there and you haven't registered yet, please do so. This is important partly for the statistics of the academy, but also for contact tracing purposes. So please go to our outreach page at the Strings webpage and click on the registration links if you want to go to this talk. I'll hand over to Stefan.
My pleasure to be the chairman of the last regular session of the conference. Start with a talk by Susanne Reffert on the large charge expansion.
Thank you very much. It's great to be here in this beautiful city, so thanks for having me here. So I will report today on a rather large body of work done with quite a number of collaborators all over the world. Let me in particular point out that yesterday you've heard already a sneak preview in Nicola's Gong Show talk. He's on the market this year. He's very smart. Maybe you want to hire him. Okay, let's get started. So the problem is strongly coupled physics. It's very difficult to access. We don't have small parameters to work with. So what do? What we can do is to make use of the symmetries of our system and look at a special limit or a special subsector where hopefully things become tractable. What I'll be doing is to look at theories that have some form of a global symmetry. If I have that, I can slice the Hilbert space into sectors of charge under the symmetry, and I will study in particular subsectors where this charge is large. And what we will see is that this charge becomes then a controlling parameter, so I can again do a perturbative expansion. So I'll be considering systems with a large number, a large quantum number, which means many degrees of freedom. And what happens is that there will be some emergent phenomena in this sector. These in turn can be described in a semi-classical description. The example we'll be seeing is a superfluid description. And the great thing about having such a semi-classical description is that it works even if our original system here was strongly coupled. So the question is our microscopic theory accessible? If it isn't, because it's strongly coupled, then we are in great shape to use the large charge expansion, and we'll write a large charge EFT, which will be an expansion in inverse powers of the charge. On the other hand, if the theory is accessible, either because it's weakly coupled to begin with, or because we take some simplifying limit, or if it's supersymmetric, then you might say, well, why would I work at large charge? I can already access the system. But if I do it anyway, if I combine large charge with these other extra control parameters that I have, I can do even more. I can go beyond the perturbation theory in the inverse charge, and I can even calculate the non-perturbative corrections. As far as we can tell so far, there seem to be two main categories for how systems behave at large charge. One is that we have a superfluid description. This happens whenever we have an isolated vacuum, and there's a number of interesting systems where this happens. The Wilson-Fisher CFT you already heard of. There's also non-relativistic CFTs, in particular the unitary Fermi gas, where this works. There are some superconformal models and the Gros-Neveu model. And the other category is that we have to write an EFT of the moduli space, which happens whenever we do have a moduli space of vacua, in particular also for supersymmetric theories. But today I'm not going to talk about that, but focus on this case here. So we look at scalar field theories. We know they have a strongly coupled fixed point between 2 and 4 dimensions. The Wilson-Fisher fixed point here, where we have a CFD, it's strongly coupled, and we'll see that we'll have a superfluid description. And we will study the ON vector model in 3 dimensions here. It looks like this. We have a quartic and a quadratic and a quartic coupling here. And, it's known to flow to the Wilson-Fisher fixed point if we tune this coupling, the quadratic coupling that just went away, to the conformal coupling. The simplest example is to just work with the O2 model. We know it flows to the fixed point. Also in the IR, we assume that we still have a complex scalar, which we parameterize in terms of a radial and an angular mode, because like this, we see directly the global U1 symmetry we have, namely, we can shift here the angular field chi. We will compactify the system in a box, and when we fix the charge, this will introduce a scale into our CFD. And given by the fixed charge here, and we will study the CFD at the fixed point between these two scales given by the compactification scale and the charge. Now, fixing the charge breaks the symmetries. We have spontaneous symmetry breaking happening. We start with the conformal group times O2 or U1, and we get, in the end, so we break the boost, we don't get any massless goldstones, and we break the global symmetry. So this gives us the superfluid description of the broken U1, and we want to now describe the dynamics in terms of a single goldstone field, which is the chi field. To leading order, we get an effective action of this form, which we can get purely by dimensional analysis, seeing that chi is dimensionless, it's a phase, and we want a dimension 3 operator. From here we can find the lowest energy solution. It's homogeneous, but it has a non-constant WEF. So this is our ground state solution. And now we want to go beyond the leading order. We want to write a Wilsonian theory. So we have to include, in principle, infinitely many operators that are allowed by parity and scale invariance. But now we can use the fact that we are working at large charge, and we can use the vacuum solution to determine how these operators scale with respect to the charge. And we find that a single derivative of chi has a positive row scaling, whereas multiple derivatives have a negative row scaling. And in 3 dimension, it turns out that there are only 2 operators that are not suppressed by inverse charges, by inverse powers of the charge. So this is a very simple description. We have the leading order term, we have a coupling to the curvature here, and everything else will be suppressed. So this is something we can actually calculate with. Now we have here 2 Wilsonian parameters, which are not accessible within the EFT. And this is our starting point. Now we can start to calculate things. I start with the energy of the classical ground state. And I still have these 2 parameters which come from here, which aren't accessible. Then I have the dependence on the manifold on which I compactified. And importantly, we have the Q scaling. So these are very large at large charge, clearly. Now I want to expand this action you've seen around my ground state, mu t plus fluctuations. I get these 2 big contributions from the vacuum, and I get basically a massless boson with the non-relativistic speed of sound here. From here I can find the dispersion relation, which is linear in the momentum, exactly as we would expect from a Goldstone. So indeed, chi is a Goldstone, and we call it the conformal Goldstone because the square root of 2 is directly dictated by conformal invariance. This was so far all semi-classical. What about the quantum effects? Are they controlled? The answer is yes. Only the Casimir energy of the fluctuations are not suppressed. Everything else is suppressed. So in summary, the EFT I have in my sector of large charges, I have a large contribution from the vacuum, I have the contribution from the Goldstone, and everything else is suppressed. Now I can actually calculate stuff. I have a CFD, I want to calculate conformal data. And I use the state operator correspondence, which states that an operator inserted in the plane corresponds directly to the energy of a state on the cylinder. This is why we like to work on the cylinder here as compactification manifold, which means, since we have already calculated the ground state energy, I already have the scaling dimension of the lowest operator of charge Q, which is simply R times the ground state energy plus the Casimir energy. So this is the result. Now let's test this prediction. This is a strongly coupled system. There weren't any things to compare with, but some lattice theorists did simulate this on the lattice, and we see it's a very good agreement. These horizontal lines are error bars that are so small that they squashed onto each other. On the lattice, you can calculate these 2 parameters, of course. It works really well for O2, and what is striking is that it even works down to very small charges, which is not something we would have expected. So where else can we apply this expansion? And the obvious generalization is to go from O2 to O2n. So let's do that. I'll just give you the results very briefly. We have now a non-abelian global symmetry, which means there will be new effects that we couldn't see for O2. First of all, before we just had the U1, which we could break to nothing. There was nothing else we could do. But now there are new symmetry breaking patterns that are possible. Also, inhomogeneous ground states are possible, but if we stick with the homogeneous case, the ground state has the same form. It's again this mu t that we get. Oops. This shouldn't have looked like this. But anyway, this is the symmetry breaking pattern where we have here the relevant point of the global symmetries that we break from un to un minus 1. Okay, this has gone really wrong. But what we expect, what happened to that slide? Seriously. Oh well, so let me just say it in words. What we expect is that we get the dimension of the coset U1 over UN minus 1. But what we find is that we have a new sector of goldstones, which are so-called non-relativistic goldstones or type 2 goldstones. They count differently. They have a different dispersion relation. They go with p square instead of p, so they behave differently from the usual relativistic ones. And we have n-1 of these, which are paired with n-1 massive particles that have mass 2 mu. Now, these have been found in the literature already by people studying non-relativistic systems. They found it counts double. And counting my modes, what do I do here? Yep, okay. So indeed, I have the goldstone we had from the O2 sector. I have these n-2 new ones, which I count double. So this works out to the expected counting. However, for the Casimir energy, they contribute only at the lower order in Q, so these are more suppressed. So in the end, the scaling dimension looks exactly the same to this order as for the O2 model. What we have here is that we have, again, these coefficients which are independent, of course, but this number here, which is the Casimir energy, turns out to be universal for O2n because it just came from the O2 sector. And this has also been verified independently, numerically. Again, we went back to our lattice friends and asked them to also check the non-abelian case. They simulated the O4 model, which is the smallest non-trivial case with the non-abelian symmetry. And again, you see this keeps working very well. There are slightly different values here. It's again a great match. Now, what else can we do? Now we can do the thing I mentioned before. We can get more control by taking the large n limit. And here we use standard large n methods. We don't use at all the EFT. The only thing that we do is that we also fix the charge now. So we start in the UV with this Lagrangian I showed before. And we know that here, if we tune R to the conformal coupling, this flows to the Wilson-Fisher fixed point with U going to infinity, but we don't have to do that. We can instead just keep U finite. And here again, the whole rest of my slide is missing, which is not very good. Can we maybe try the other slides? Or
I can try to re-download it.
Yeah, maybe try to do that. But so I can go on in words what is supposed to be happening here. So it's large n. I do a Stratanovich transform, which means I introduce a collective field, which I call lambda. And then, since I fix the charge, I also introduce a covariant derivative, which contains the chemical potential. And after the Stratanovich transform, we will see that the phi field, the action became quadratic in phi. So I can integrate out completely the phi to get an action just in terms of the Stratanovich field lambda. And so yeah, let's give this. This looks maybe better. Let's see.
Kann ich die andere, die alte Version auch nehmen?
Ja, die ist gut.
Okay, das ist doch das.
You can use the tangent, right? Formulas.
That is true, yes. So anyway, I can integrate out the field phi, and the collective field lambda will get a VEV, which is m square. M was my chemical potential. Well, let me just go on with the slide as it is. Most of it seems to be fine. So I said in words what happens. Okay, let me just jump forward to the large n story. All right, so yeah, I did the transform. I got here m square, which is the VEV of the Stratanovich field, and I get now a Lagrangian. And we see that we have two terms here, and if I, instead of the sphere, work just in flat space, which isn't appearing here, this simplifies to this term. And this is a term that would go away at the critical point, because u goes to infinity. So in the CFD, I only have this guy. Away from the critical point, I also have this guy here. And what's missing here is that if m is exactly, m squared is del mu chi, then this is exactly the nonlinear sigma model description that we have seen in the O2 model. So what I want to do is to go from this nonlinear sigma model description to a linear sigma model description. I want to extract the effective potential to make things a bit more transparent. And again, my formulas are missing. And okay, nothing is happening. Okay, this is really not... they're all missing. So needless to point out, this is the first time this ever happens, and it has to happen now. So anyway, what does happen, what you can't see, is that it turns out that the linear sigma model is related via Legendre transform to the nonlinear sigma model. So I can find the effective potential by just taking the Legendre transform in this VEV m square of the Lagrangian that I showed you on the last slide via this supremum formula. And then depending on the value of the quadratic coupling R, I get three cases. The first is the unbroken phase, where this is the tree-level potential, which is just the naive one. And the red line is the effective potential that I calculated via the Legendre transform. It's here. It's quadratic here. Then R equals to 0 is the critical case, where I have a flatter potential, but they're still more or less the same. This is a sextic potential here, which is also something one can see directly in the O2 model, in the linear sigma model. And R smaller than 0 is the broken phase, where the naive tree-level potential has this usual double well form. But we know that the true effective potential that includes all the quantum corrections always must be convex. And that's what we're seeing here, thanks to this supremum definition of the Legendre transform. So outside of the two minima, there's just this formula that is not here now. But in between, it's flat because of this supremum. So we got this really nice physical description here in a very simple way, just by realizing that we could take this Legendre transform. So let's see. All right. So let's now go back to the critical case, meaning we put u to infinity, and we want to again calculate the scaling dimension, and we find this formula here, where we see the same scaling that we had gotten in the EFD. So that's the same. This is in leading order in large N. But what we see here is that we can do more. First of all, we can calculate here all the suppressed corrections, but we can also calculate the numbers here. These are C3 halves and C1 halves that within the EFD we couldn't calculate, but thanks to the large N combined with large charge, we can calculate them all now. And what is also nice is that we could do that without having to evaluate lots of Feynman diagrams, but in a very straightforward manner. So, okay, these things are there, other things are not there. But since I have now the power of large N and large Q, I can go beyond verifying the results that I had in the EFD. I can find these coefficients. The second one didn't show up, but you've seen them on the slide before. There's also some new lattice data calculating these coefficients. This looks fairly good. Remember that this is n equals infinity, which is not exactly what they have on the lattice, so it's looking pretty good. And since we have now all the coefficients, we can do a resurgence analysis. And what we see is that this large charge expansion at large n is an asymptotic series which diverges, as Nicola mentioned already yesterday, as 2L factorial. And we can write the non-perturbative corrections, which is something we couldn't have done if we hadn't also gone to large n. And we find this form here. And this is interesting because this allows us a geometric description, which is not coming here, but what we see is that this is basically the action of a particle propagating on the equator of a two-sphere, and it has mass 2 mu. Mu is square root of q. So we have now a geometric description. Combining the geometric description with the fact that we have a CFD and no other scales, this leads us to believe that this description must hold not just at large n, but for any finite value of n as well. And then we can find the optimal truncation of this asymptotic series, which would be on the bottom of the slide. And if I remember correctly, it goes as order of square root of q. And this is an explanation for why this lattice plot worked so well down to small charges. Because if they went to, say, charge 9, which means that you have to include up to 3 terms here. So that's the explanation ultimately why this works well. So far, all I've been saying was in 3 dimensions, but of course you can apply the formalism also to the general dimensions. And this Lagrangian I showed you before at large n in general dimensions looks like this, where we have this gamma function. And to see the behavior, it's enough for us to just plot this for several dimensions. Oh.
Einfach umsteigen.
Okay, better late than never. If you have questions, I can show you the broken slides later on. So, yes, so this is my gamma function. And I see that everything is fine with my Lagrangian between 2 and 4 dimensions. We've been working at 3, but between 4 and 6, things don't look so good. But so the Lagrangian is unbounded from below. There's clear an instability, but we can still turn the crank. We can formally compute the conformal dimension in 5 dimensions, and we get this expression here where there's several branches for these f's, but we see these are all complex. So we can still say, okay, we can interpret this as a non-unitary CFD if we're so inclined. This has been seen by other people in the literature, but via this expression it's kind of obvious that things don't look so good between 4 and 6. All right, so let me summarize. What have we seen so far is that we have seen some very concrete examples where strongly coupled CFDs simplify in a very important manner at large charge. We've looked at the O2N model in 3 dimensions, and we have computed the conformal dimension in a controlled perturbative expansion here at the fixed point. There's excellent agreement with lattice data for O2 and O4, where O4 was this non-abelian case, which was more interesting because we had 2 kinds of goldstones, which is due to the fact that the boosts are broken when we fix the charge. And then in another step, we combined large charge and large n. Here we didn't have to work with an EFT, but we could directly expand around the subtle point. We have more control than in the EFT. We can control the coefficients of the large charge expansion. And this allows us, on the one hand, to go away just from the fixed point, but look at the entire flow here. And we can extract that effective potential in a very simple way. Again, without having to evaluate a lot of diagrams or anything. Now, this is the further direction slide, where I also quote other people's work. There's a lot of other things that I didn't have time to go into today. There's the whole class of superconformal theories that have been studied to a certain degree, up to one-dimensional moduli spaces. Higher dimensional are in the works, but hasn't been published yet. Then, of course, you have a CFD at large charge. What would the gravity dual look like? That's a very interesting question, which has seen some progress, but I think there could be there's a lot more potential for new interesting results here. Then people have looked at operators which also have spin, the group of Ratazzi in Lausanne. Of course, it would be also interesting to now study directly dualities where we have a handle on the strongly coupled side. So maybe one can use that to check dualities, to find new dualities. There has been some cross-checking with results of the conformal bootstrap. Of course, you can always simulate more stuff on the lattice, higher n inhomogeneous ground states, etc. You can start studying different dimensions than the 3 and 5 that I mentioned briefly today. People have looked at Chern-Simons matter theories at large charge. Then in another way of combining a control parameter with large charge, people have been studying the Wilson-Fisher fixed point in 4 minus epsilon dimensions, which again allowed them to find things perturbatively, not just in the CFT. You can try to go away from the conformal point, either as I've shown you, at large n, or also in different ways. Then there's this entire class of the non-relativistic CFDs, which is also very interesting. These aren't actually CFDs, but systems with Schrödinger symmetry that quant-math people are interested in. In particular, there's this unitary Fermi gas, which can be realized in the lab and which also has a superfluid description. Then there has been work on boundary CFDs at large charge. There's been recently a connection to the weak gravity conjecture. And of course, it would be very interesting to study fermionic theories. So, yes, that's what I had to say. Thank you very much for your attention.
Very much for the talk. It was a pity that we didn't get to see all the slides, but maybe that's a motivation to look at the papers. Other questions?
Thanks for the talk. You mentioned.
Oh, no. Just.
You mentioned the work of Ratazzi on the spinning vortices.
Yes.
I think a certain spin.
Say again?
They couldn't continue it beyond a certain spin.
That's true.
So does large n resolve this puzzle?
It's a very good question. We haven't looked at it, but it would be an interesting way to try. Yes, absolutely. But I don't have the answer because I haven't thought about it.
Questions here?
Maybe try this one.
Hello? Great. So what additional information do you need in order to fix the large charge expansion? So I understand, like, for instance, for the O2 model or for the O2 universality class, there's a universal prediction, and then there's the terms which are kind of model dependent. And so in the case of this comparison to, say, Monte Carlo data, you fixed some of those theory-dependent terms, and then you got a nice fit which matched other results. But I'm just wondering, like, is there some minimal set of data which, if you had that, would be enough to fix the large charge expansion to all orders for a specific theory?
I'm not sure. So, are you asking? So that's, by the way, the Resurgence slide with the picture that didn't show up. Anyway, so let me jump back to the slide with the MC data. So what? So this is also this was a really nice slide. Pity you couldn't see it before. But yeah, I don't manage. Maybe on the computer, can we jump further back? Right. So what people did exactly on the lattice, they calculated this actually in two ways. One was by inserting operators of a certain charge and calculating the correlation function. And then I think they also calculated directly the scaling dimensions. But I'm not totally sure what
No, so I'm asking from your perspective. So you have a large Q expansion. I understand that some of those terms are universal, and some of those terms will be different depending on the specific theory you're comparing.
Yes.
And
Okay.
So I'm wondering, like, do you know, like, how many, like, numbers you would need to fix to then be able to get the large charge expansion to all orders, just theoretically, for a specific model?
So the only thing that is universal is this number here for the Casimir energy. Then what is not universal are these coefficients here. And the scaling with Q depends on the dimension, but that's for the Wilson-Fisher point, this also looks the same. So what they did was that they just did a 2-parameter fit here. They didn't have enough resolution to actually verify that number here. So
it's okay, we can talk.
I think, maybe we talk later.
So I noticed that the expansion depends on the ratio of Q and N in the large Q, large N.
Absolutely, yes.
It seems like the expansions might not commute. So what happens if you do it the other way around?
So you can do different things. So in fact, the expansion parameter, you see that in the result here, just a sec, is Q over N, and you can take it large, or you can also take it small. You can look at a small charge expansion when you add large N. And the Resurgence analysis interpolates between the two. So if you have large N, you can access both the large and the small charge regimes.
Can you make some comments about generalization to non-conformal theories? What can you compute? What physics can we extract?
So you want some remark about non-conformal theories? Like as in going away from the conformal point? Or so the easiest was what I showed you here, this story, that when I have extra control like large N, then I can just look at the entire flow. So that's the story I showed you. A different way of looking at it is you start from the linear sigma model where you have a radial mode and the angular mode. The radial mode will integrate out when you go to the nonlinear sigma model. But you could give to this radial mode, you can realize it as a dilaton. And you can give a small mass to it that explicitly breaks conformality. So this is also something we studied, that we gave it a small mass, and what we've seen there was that there was a log term that appeared that was basically the signal of having broken conformality in this very specific mechanism.
No more question then. Let's thank Susanne again.